All right, thanks, Josh, for this opportunity to describe to you a concept that's called ORCAS, the Orbiting Configurable Artificial Star, that we think will allow Keck to do great new adaptive optics in the optical and also improve the adaptive optics in the infrared. This is an effort that's led out of Goddard Space Flight Center. Yeah, I know how to do that. There we go. By Elliot Peretz, John Mather's involved in this. Goddard is leading the flight hardware. The development path for the adaptive optics is the basic thing that SSC has been going along. So there's we need to take advantage of all those upgrades. And then we have contributions from a long list of scientists. This is just some fraction of those, but I've highlighted the ones that are outside Goddard that are in the rest of the Keck community. So the concept is pretty simple. You have a spaceborne laser, and I'm going to use my laser pointer the wrong way to actually point at it. There we go. Come on. All right, so we have a spaceborne laser up here that would direct a laser beam towards Keck. Actually, all of Mauna Kea would be about a 6-mile radius. And the Keck and its AO system would intercept that, lock on, as the object is approaching the isoplanatic patch of the target. It'd be about 5th magnitude. That's pretty much set by not wanting to be easily spotted by people looking at it. And then it would maintain that position for a couple of hours within the isoplanatic patch. And so it's like having basically your own natural guide star next to a target that you like. And the reason to do this is not a surprise to most people who do AO at Keck. Keck still has a lot of potential down here compared to other assets. There's Keck today, but we now have JWST, ELTs coming, as John described, but there's a lot of area in here, both in angular resolution and sensitivity, that we ought to try to take advantage of. And one of the keys to doing this, right, you think, oh, well, I've got an orbiting satellite, it's going to be moving all the time. But there's a lot of work done on star shades and the like. And so if you have the right kind of orbit, this high Earth orbit, then at apogee, you get what is called an astrostationary position, where the angular rate is extremely slow. And it turns out then there are 2 others that are a little shorter in time. So you get 3 opportunities altogether in roughly a 4-day orbit to try to look at a target. Now, while you're going along on this orbit, you have to apply a little delta V in order to say, well, I want to do this target, and so I need to tweak the orbit a little bit and get it over to that target. And there are, of course, limitations on how you can do that, which I'll describe in a bit. But this is an example of ORCA's approaching its approach path, gets within an isoplanatic patch. You turn on your AO for science and take a couple-hour observation, or, you know, it can be shorter or longer a little bit depending on the declination of your target. Right, so here's the estimated boost from Peter Rusinowitz. This is for the galactic center here. And you can see there's quite a substantial gain in the optical, but it keeps going all the way to the wavelength range where Keck has instruments or plans to have instruments. And how does it really do that? Well, for any target, right, you have more photons, so you can support more sub-apertures, like the high-order deformable mirrors. And you could tune the system to have lower lag. And it reduces the non-common mode path, right? So your non-common path of the light is going through almost the same light as your star, rather than going up and you get the scattering coming down. And as I said, it's steerable, so you get a nice bright natural guide star, essentially, or artificial guide star. Okay, so how would we exploit this? Well, the list here of example science inputs wouldn't be a surprise to anyone. It's kind of a list of things people have been trying to do with adaptive optics for a long time. AGN, high redshift universe, exoplanet solar system. The things that might be somewhat new to people is you can now really think about using AO to go after very faint targets, because you've essentially suppressed the background sky. And this is my special interest because I'm interested in doing supernova type 1a cosmology. When it's not out there at one of its opportunities, there are these opportunities to do flux calibration, what we have spun that off into another engineering design test. So these are just some examples. Again, this is a slide that Peter put together of a large number of Gaia stars and looking for planets around them. So this example with scales, Haka, orcas, so all in the future. But you can see what JWST can do, what scales plans to do on its own. But then you can still get this considerable improvement if you can run orcas. This is an example of a flight path if you want to go around and look at all these Gaia stars, right, where you'd have apogee at these different locations as you go throughout the year. And at some point, you run out of fuel to do the delta Vs. And then there are these side opportunities, and there may be interesting targets near those as well. So as I said, my main interest really is in the time domain astronomy. So one way you can use this instead of moving all over the sky is look in a fairly concentrated field like Roman or LSST would have, a few square degrees, and say, well, someone tells you there's a transient, you do the delta V a couple days later, Orcus comes sailing in, and when it gets in the isoplanetic patch, you can observe it with any of these nice instruments that we expect to have on Keck. And you can keep doing this every orbit. So Friday, you hit a different one. And you can just keep doing this for any kind of transient. So that's one of the other modes besides sailing around the sky. And although right now I'm just describing, well, one mode, you could have several of these satellites ultimately once we do the technological demonstration that this will actually work. We're even toying with, and this is where we'd welcome more feedback of cool things you could do with this. There's an isoplanetic patch that Orcus traverses right along here, right, as it's sailing along. It's going relatively slowly, and within that, you could do AO. And it works out that if you did an isoplanetic patch width that was 1 degree long, that'd be like a NIRCam observation. But maybe you could do it way down in the optical. So these are just some of the ideas that we're playing with. There are some things that are solid and some other things that are, well, this could be fun for some people who just want statistical views of the sky, what a galaxy population look like. They don't have to get it in a rectangular field of view necessarily. Well, this is just mostly a concept, but we're moving forward with a lot of the technological demonstration. So some of the technology needs to be demonstrated on small sats. The Keck AO upgrades need to move along the path that they're currently moving on. And Peter just said, well, he got money to do Haka now, so things seem to be moving along there. I mentioned that for the flux calibration, we've spun that off into an engineering demonstration unit that we're also talking about flying. And there's work on actual instruments, which might surprise people. So I'll describe in a minute ORCID, which is the Orca's Keck instrumentation demonstration that's operating now. Then Peter has some observations that have tested with ORCID what you can do on stationary targets or using A-pulses, so using an asteroid that's bright enough and moving close to an object. And then we're doing some preliminary design work on ORCID 2, which may be a visible plus near-IR integral field spectrograph. So here's some more information on ORCID. It's a tiny little thing. That's one benefit of adaptive optics is your instruments get to be pretty tiny. And so it sits right here on the Keck adaptive optics bench. And this was all put together and put into operation in about a year. So that's one of the things we're trying to do is just move fast and basically learn by doing. So this is an example that we get near diffraction limited here. And this is not with all the advances that I talked about, right? This is just using Keck AO as it stands today. You can already get some interesting data. So for more information on the talk or the orcas concept, there are a few people here, myself and Peter, a few people who may not be here. You can talk to any of them within the Keck ecosystem. We did write a big, long report. It's about a year or two old right now. You can read that to go all the way from what could you do scientifically to how you do the technical implementation. And then a number of other documents here, including a couple of white papers that were submitted on instrument concepts, or this general notion of how do we make a hybrid ecosystem, where instead of space and ground one following what the other has found, they work in concert with each other. So I'll conclude there and take any questions. Thank you.